Hi, I'm Jalen, and I'm presenting SageDB, an instance-optimized data analytics system. This is work done mostly at MIT. So in 2019, some authors of this paper, and others, proposed a vision for SageDB, a learned database system that can automatically optimize itself for any given use case. Now, over the past few years, we've been building SageDB as a real system, and today I'm presenting a first prototype of our system that's focused on analytic workloads. So there's been a lot of work in our community on learned database components, spanning learned data structures like indexes and Bloom filters, to learn algorithms for query execution, to learn query optimization, and much more. And for the first version of SageDB, we decided to incorporate two of these components, namely data layouts and computation reuse. So I'll first introduce what I mean by instance-optimized data layouts. Let's imagine that in your database, you have this table with two columns, age and salary. Now, for illustrative purposes, we're going to visualize the rows of this table as points in multidimensional space. So here, the x-axis represents age, the y-axis represents salary, and every point represents a record in the original table. Now, let's say a user wants to run this query. Compute some aggregation over all points that satisfy the given filter. And to execute this query, we essentially need to find all points inside the green rectangle. The simplest way to do that is through a full table scan, but that results in a lot of extra scanning over points that are not relevant, which I've shaded in red. And this extra scanning hurts performance. So one very common way for systems to reduce the amount of scanning is to lay out the data using a single column sort order. So for example, if we sort all the points by age, we can restrict our scan to only the points that satisfies our filter over age. However, this doesn't help us filter over the salary dimension, so we still end up scanning a lot of extra data. And of course, if we instead sort by salary, we end up with essentially the same problem. So instead of sorting by a single dimension, we can imagine a data layout based on a multidimensional grid, in which points in the same grid cell are clustered together physically. This enables us to find the desired data with much less scanning by restricting our scan along multiple dimensions simultaneously. Now, it would be hard for a database administrator to manually select the best grid layout, since it requires carefully selecting how many partitions to create in each dimension. So the idea of instance-optimized data layouts like Flood, which was published a few years ago, is to automatically configure the grid layout to maximize performance for a given dataset and workload. So given a workload like this, with two queries visualized in green, Flood can automatically configure a grid to minimize scanning on that workload. And given a different workload, Flood automatically configures a different grid specialized for just the queries in that workload. And this example shows that instance optimization requires two steps. First, Flood increased the degrees of freedom by sorting by a grid instead of by a single dimension, which increases the number of possible configurations. And second, Flood introduced an optimization algorithm that automatically selects the best configuration given a use case. So both of these steps are necessary for instance optimization. Note that if we just did the second step, it would be auto-tuning. So besides Flood, there's been a lot of prior research on instance-optimized data layouts in our community. And our paper presents a new instance-optimized data layout technique. The key idea is that instead of optimizing the layout of the original table, we create multiple partial replicas of the table and optimize the layout of each partial replica for a different subset of the workload. Then at runtime, queries are routed to the replica that would minimize scanning. Now, for the sake of time, I won't go into further detail about our replicated data layouts during this talk. Besides layouts, the other component we integrated in SageDB was computation reuse, which refers to performing a computation once and reusing it for future queries. And the most prominent example of this in commercial systems is materialized views. And while there has been work on auto-tuning and auto-selection of materialized views, there's been little research work on instance optimization for computation reuse. So we fill this gap by introducing instance-optimized partial materialized views, or PMVs for short. Now, in addition to introducing these new instance-optimized components, the second contribution of our paper is an optimization algorithm that co-optimizes these two components under a global budget. So I'll first talk about PMVs and then about our global optimization algorithm. Now, before diving into PMVs, I'll first talk about how materialized views are used typically in commercial systems today. So typically, materialized views are used to substitute parts of the query plan. So instead of reading from a base table, we read from a materialized view. So for example, imagine that the workload consists of queries following this template, which is two parameters in the query filter represented by question marks. And by replacing the two question marks with actual values, we would turn this template into an actual query. Now, in commercial databases, it's common to create materialized views or query templates by moving the columns involved in the parameterized filter, which in this case are type and timestamp, into a group by like this. So using this materialized view, we can transform the original template into a new template that returns the same result, but reads from the materialized view instead of the base tables, which can result in better performance. However, materialized view usage is typically a binary decision, meaning either we read the materialized view or we read the base tables, but not a combination of the two. And this limits their flexibility. So our idea with partial materialized views is to allow answering part of the query using the partial materialized view, which results in a partial result, then send the remainder query to read the base tables, which produces the remainder result, and merge these two to form the final result. And as I'll show in the following example, this gives us a lot more flexibility to trade off query performance for storage space. So let's say we have the sample template as before. A partial materialized view is logically represented as a grid over the joint data space of the columns involved in the parameterized filters, in this case, type and timestamp. And each cell of this grid contains the result of executing the query over just the data represented by the cell. So for example, the green highlighted cell represents all data where type equals C and timestamp is less than 10. And the green cell contains the result of executing the green highlighted query, which only executes over the data that the cell represents. Now imagine we substitute values into the template parameters to produce an actual query, which filters for type equals C and timestamp less than 30. And the query's filter is visualized in blue, and the query execution flow is shown on the right. So SageDB at runtime is able to automatically detect that two PMV grid cells are subsumed in the query filter, namely the two highlight cells in green. Therefore, we extract the partial result from these two cells, which leaves us with a much smaller remainder query whose filter now excludes the data covered by the partial result. Now, executing the remainder query is much faster than executing the original query due to scanning, joining, and aggregating less data. And now finally, we merge the partial result with the remainder result. So this example illustrates the benefit of partial materialized views. They increase the configurability of the system by increasing the degrees of freedom. A finer grained PMV grid takes more storage space due to storing more partial results, but produces smaller remainder queries that are faster to execute. Whereas a coarser grained grid takes less space and produces more expensive remainder queries. So by controlling the granularity of the PMV grid, we can trade off storage space for performance. So now that we have a highly configurable component, how do we configure a set of PMVs to achieve the best performance for a given data set and workload? So we developed an offline algorithm in which we assume we've collected some history of the user's workload, and the objective is to choose a PMV configuration that minimizes the total cost of executing the workload under the constraint that the total size of all PMVs must be under some storage budget. So in SageDB, each PMV is associated with a particular query template, and some query templates might be more expensive than others, and some might be used more frequently than others. Now, the search space of configurations that we're choosing from, in other words, the degrees of freedom we have, are that a PMV for a particular template is parameterized by the number of partitions along each grid dimension, and we assume that the partitions are equally spaced along that dimension. So for example, for template A, the first candidate PMV I've drawn has 2 partitions along each dimension, and template B has candidate PMVs with 3-dimensional grids. And in general, there are an extremely large number of candidate PMVs for each template of varying sizes. So to simplify the optimization algorithm, we break it down into 2 challenges. First, given a single template and storage budget, how do we find the best PMV grid for that single template? And then second, how do we divide the total storage budget among the different templates that appear in the query workload? And for the sake of time, I'll only focus on this second challenge during the talk. So if there are n templates, then we have an n-dimensional continuous search space of possible ways to divide the total budget among the templates. And exploring the search space through black box optimization techniques can be very expensive. So our key insight is that for a given template, creating a finer grained PMV, meaning a PMV with more cells, has diminishing marginal utility. So to give you some intuition for what that is, imagine that we have this very simple query template that filters over column A. Now, if we don't have a PMV, we would need to scan and aggregate nearly all of the data shaded in blue. If we did have a PMV with 2 cells, we would need to scan and aggregate around half the data because the cell on the left is subsumed and would be removed from the remainder query. And if we have a grid with 4 cells, we can scan around 1/4 of the data. So we can extrapolate this and say that the cost of a query for a PMV with n cells is approximately 1/n, where cost here is essentially the amount of data read, and this is a convex function. Now, given this insight, our algorithm is to iteratively explore the cost functions of all templates simultaneously, starting from each template having a budget of 0, and then iteratively allocating a small amount of storage budget to the template for which the extra space would reduce cost the most. So here's an example of how we essentially explore the template that gives us the steepest descent towards lowest cost. Now we configure this step size in such a way that the overall complexity of this optimization is linear in the number of query templates in the workload. And here, cost is over all queries in the template, not per query. And so the cost accounts for any differences in the frequency that each template is used. So now that I've explained instance optimized PMVs, I'll now explain how we co-optimize our two components simultaneously. Our global objective is to minimize cost for the query workload according to our internal cost model under a given memory storage budget and disk storage budget. Now in SageDB, we store PMVs in memory and partial table replicas on disk. So their storage budgets are actually independent. And at first it appears that no global optimization is necessary. But in reality, it would be a mistake to optimize each component individually. And that's because recall that only the remainder queries will access the base tables or replicas. So we need to make sure that the replicated layouts are only optimized over the workload of remainder queries, not the original query workload. And this depends on what PMVs exist. And furthermore, the benefit of having a PMV depends on how efficient the remainder query is to execute, which depends on how good the layouts are. So the definition of cost for PMVs depends on the layouts. And therefore, we cannot simply optimize these two components independently. Therefore, SageDB performs a global optimization by iteratively holding one component constant while optimizing the other, doing this in a loop until we reach convergence, meaning until the cost does not decrease from one iteration to the next. So now I'll explain the overall workflow in SageDB. Base tables are stored on disk and users issue queries against these base tables. Our rule-based query optimizer has nothing to do because the only choice is to read the base tables. And at any point, the user can run an optimize command with a given storage budget, which will trigger SageDB's global optimization algorithm using the query workload history, and the optimized layouts are stored on disk, and PMVs are cached in memory. Now for the same query, instead of reading from the base tables, our query optimizer will first try to use any PMVs that exist for the query. In this case, imagine that we obtain a partial result from the PMV for template 2. The remainder query is now much faster to execute. Our optimizer then tries to substitute the base table scan with scans over the replica that would minimize cost. This reduces scan cost even further, and then any remaining scans will go to the base tables. Now, in terms of results, we evaluated SageDB across 3 different datasets, including a real-world dataset and workload from the gaming division of a large technology company in the leftmost plot. We evaluated SageDB both out of the box and after the PMVs and layouts have been optimized. And we also compare against a popular cloud-based commercial data warehouse, which we call SystemX, in both its out-of-the-box configuration and a tuned version, where it has been both manually tuned and auto-tuned. And overall, SageDB is up to 3x faster than the tuned version of SystemX, and is up to 250x faster on individual query templates. And the kinds of templates where SageDB gets the biggest speedups are templates like this, which have a very expensive join over multiple tables and a filter over a high cardinality column, which prevents traditional materialized views from being effective, whereas SageDB is able to use partial materialized views in combination with scans over partial table replicas to achieve better performance. And furthermore, what's interesting is not just the direct performance comparison between these two systems, but also the relative comparison of each system against its unoptimized self. So the gains produced by SageDB's instance optimization, represented by the difference between the light and dark blue bars, is up to 10x more effective than the gains from tuning SystemX's materialized views and sort orders, both through manual tuning and auto-tuning. So as I mentioned at the beginning, this paper was just a first prototype of the SageDB vision of a learned database system. And in terms of next steps, as many of you probably know, most authors of this paper, including myself, are now at AWS, continuing our work on instance optimization, including of data layouts and materialized views. And when comparing SageDB to production systems like Redshift, we found that data and workloads actually change quite a lot in practice. So in fact, around 50% of all commands in Redshift are inserts. So now there's quite a lot of emphasis on adaptivity and auto-remediation when designing new instance optimized components. We also found that while individual queries can be highly complex, there's actually a lot of patterns between queries, and around 80% of queries are repeated, which is great for instance optimization. So there's not much more I can say publicly at this moment, but you will be hearing more from us in the near future. We're also hiring, so please reach out if you're interested. Thanks for your attention.